All right, here we go. We've got a question, a classic question, or classic context, I would say, for angular momentum. What we're doing here is we're looking at the ice skater spinning, and what we notice is we have their arms extended, and we then pull their arms closer to their body, and we're wondering what happens there. As ever, press pause, try the question, and when you're ready to see an explanation, press play. All right, so as I say, this is sort of a classic context. We use this very often. You may have done this demonstration in one of your classes where you may be sitting on a chair and looking at momentum changes. First thing to notice here is we've got frictional effects that are negligible. Now this is really important because what that means is we can apply the law of conservation of angular momentum here. In other words, I1 omega 1 equal I2 omega 2. This is similar to the conservation law of linear or translational momentum. However, I think that people often forget about both of these laws is that there's under one condition, well, one main condition, which is an isolated system. There is no external force occurring on our skater, and in the case of a car collision, something like that, it would need to be no external force there as well. This allows us to do this. And what you'll notice there is you make I smaller, omega increases, so this skater is going to start spinning faster. So immediately we can say that one is true because of the fact that friction effects are negligible. And we're going to go through them, but hopefully you can see actually there's another one we can get rid of straight away, but we'll come to that. Let's look at the second one, rotational kinetic energy. This has two forms, half I omega squared. Okay, that kind of tells us something. It looks like it won't change, but a really good one is this L squared over 2I. This is the total angular momentum over 2I. Now notice we are changing I, but we're keeping L the same, and so therefore the rotational kinetic energy does not remain constant. I is increasing or decreasing. In this case it is, let me get this right, decreasing, and so therefore the kinetic energy is going to increase. So actually this means we can get rid of both of these answers here, and we're left with B. Now why is 3 true? Well, again, this net torque acting on this ice skater 0 really is the equivalent statement to what I've just said about no external forces. No external forces means no external torque, and no torque acting on the body means that our net torque is 0, which means we can apply the laws of conservation of momentum. So really you've got a chicken and egg situation here. That's not particularly satisfying for me, however, that's why the answer here is B.